In this lesson, we're going to look at a few different word problems that you might need to use exponential or logarithmic techniques to solve. So, to start off, we have a couple of formulas that lend themselves really well to exponential or logarithmic solving because they involve exponents. And we can often solve these problems without exponential or logarithmic methods because we're not trying to find a variable in the exponent. But if we have a variable in an exponent, we're going to need logs in order to be able to solve this. So we have the first one, which is our half-life growth or decay, which is often used for things like half-life. So we have growth or decay. And that is, we have A equals A naught times X to the T over T. When we use these formulas, we also have to remember our order of operations. Remember that exponents come before multiplication, and we're going to see as we solve these that that can sometimes be an issue. So this is the total time the item is left, and this is the time of growth or decay. So something like a half-life would go there. Okay, the final amount is A. And our initial amount is here. Okay, and your X is your growth or decay value. So for example, a 20% increase would be 1 plus 0.2 or 1.2. And a 10% decrease, just like with those sequences and series problems, would be 1 minus 0.1 or 0.9. The one that you're going to see a lot is half-life. That would be 0.5 because we're looking at when it's decayed to half of its initial value. Okay, so the next formula we're going to be using sometimes is the formula for compound interest. And so we have, for compound interest, A equals P times 1 plus R to the power of N, for NT. And generally interest rates, so interest rates, these are usually going to be an annual interest rate. Might be another time period. Our N, which means the same thing in both places, is the number of compounding periods per length of the interest rate. So if you're talking about annual interest rates, which we almost always are, especially if you're using actual real life scenarios. If your compounding period is monthly, then N would be 12. If your compounding period is daily, it would be 365. So example, a lot of accounts you have might compound on a monthly basis, whereas credit cards often will compound the interest that you owe them on a daily basis. And so T is the number of years, or if the rate is not in, or whatever length of rate is. So usually those rates are given as a yearly rate. P is your principal or initial amount. It's your starting amount. And A is your final amount. So this is how you calculate the actual amount you would end up with given a certain principal, a certain interest rate, and a certain number of compounding periods per rate. Okay, so we're going to look at a few problems. We're going to look at one that doesn't involve any of these, and then we are going to look at a couple of problems, one with compound interest and one with half-life. So with a growth or decay formula, and in this case, half-life is decay. Okay, so first example 1. And please pardon my handwriting. A lake is stocked with fish. This happens so that people can actually go fishing. They'll put fish in the lake. The initial amount of fish is 10,000. So they started by stocking the lake with 10,000. And the fish population increases by 3.5% yearly. How long will it take for the number of fish in the lake to double? So we can think of this is a growth problem. We don't necessarily have to use a growth formula, but we can think of it almost like a geometric sequence. So we've got our fish population is equal to 10,000 times 1.035. This is our growth factor. Okay, and I'm going to let t equal the number of years. Okay, so it's going to be to the power of t, because we don't actually have the year is the total amount of time the item is left. The time of growth or decay we're looking at, it's increasing by the same number of time that we want to report our answer in. So it's just a t. So t is the number of years. So how long will it take it to double? Well, that means we want our f, our total population here, to be 20,000. So 20,000 is 10,000 times 1.035 to the power of t. Okay, so now here is our issue. This is the biggest mathematical mistake I see people making. We can't go ahead, you're like, oh, exponent, let's log both sides. Let's log both sides. We're going to do that. Hold on. It's okay. Take a step back. Order of operations says that this exponent piece happens first. So in order to be able to take the log of both sides, we don't know, there's no log rule for splitting up a product inside a log. We can split up, well, there is, we can add the log of 10,000. Actually, there is. I lied. You can add the log of 10,000 plus the log of t, but we can't divide first. So what we're actually going to do is we're just going to get rid of the coefficient. It's the easiest way to deal with this. And we get 2 equals 1.035 to the power of t. So when you take the log of both sides, you don't really want there to be a coefficient unless you're ready to split those up, and then you're going to have more decimal numbers that you have to deal with. So now we're going to take the log of both sides. I'm going to just take the log base 10 because that's on my calculator, so it's easy to get a good decimal approximation. So we've got log of 2 equals log of 1.035 to the power of t. Now we're going to bring that t down. So we get log 2 equals t log 10, using the log rule about exponents, which is our little magic trick for dealing with exponents, variables in our exponents. And now we're going to divide both sides by log 1.035. Now we get t equals this lovely log 2 over log 1.035. Well, luckily we have calculators, and so that gets us t equals 20.149 approximately. So now, because this is a word problem, we have to answer the question. It will take 20.149 years. We have to be clear about our time period in our unit for the population of fish to double. And so that's a simple problem. It's not exactly a formal growth problem, but it is something that can be solved using our growth formula. Okay, next problem we're going to do is a compound interest problem. And compound interest can always be a fun thing to deal with. Particularly when it's in your favor. When it's not in your favor, like a mortgage or a credit card debt, it can be a little bit less fun. So let's do a fun example where we're getting money instead of owing more and more money. So we have David inherits $10,000 and invests it in a GIC at 6% compounded semi-annually. So the 6%, if it doesn't specify, you can always assume that your interest rate is an annual interest rate. And this problem doesn't specify, so we'll assume it's happening the 6% is that you get 6% a year. How long will it take for the GIC to be worth $11,000? Okay, so we're going to use our compound interest equation, which is A equals P 1 plus R over N to the NT. So let's see what we've got. So our principal is what he's starting with. That's $10,000. We want our end dollar amount to be $11,000. Our annual interest rate is 0.06. We always have to write our percentages as decimals. N is the number of compounding periods per length of the interest rate. So N is equal to 2. And our T is the variable that we're going to try to find. So let's substitute everything into the equation. So we get 11,000 equals 10,000 times 1 plus R over N. So that's 0.03. R over 0.06 divided by 2. And N times T is 2T. So again, I'm using N in 2 places here in this equation. So now I'm going to divide both sides by 10,000. So I get 11,000 divided by 10,000, which is 1.1, equals 1.03 to the 2t. Now I'm going to do what I did with the last one, and I'm going to take the log of both sides. So log 1.1 equals log 1.03 to the 2t. Now we can bring that exponent down using our log rule for exponents. We get log 1.1 equals 2t times log 1.03. And no, you don't have to show both of those individual steps every time. If you have the hang of it, that's fine. And now I'm going to divide both sides by 2 log 1.03. Get rid of our 2 log 1.03. And I get T equals a calculator problem. So you go to your calculator and you're going to punch in log 1.1. And you can use ln too if you want. The answer should come out the same no matter which base of a log that you would pick. So log 1.1 divided by 2, and then divide by log 1.03. And you would get 1.61 is your time. Now, to answer the question, we actually have to go back and think logically, because you're not going to be able to invest something for 1.6 years. So you get your 3% payout after every 6 months if it's compounded semi-annually. But if you have it in 1.61 years, that means it won't quite be $11,000 at that 6-month mark. So in order for it to be $11,000 or more, you would have to actually wait for 2 years. So we're going to answer this. It would be worth $11,000 after 1.61 years, but in actuality, in real life, after 2 years would be when that interest would actually be paid. So we do need to think, generally an answer like 1.61 years I would accept, but if you're really looking to kind of extend your thinking, think about how that would play out in the actual real life scenario if you tried to do that. Okay, last problem, and this one we're actually going to be doing a half-life problem with that growth or decay formula. Okay, so our example, let's actually write the word example number 3. Okay, we have a radioisotope, iodine 131, which will abbreviate I-131, is a radioisotope that is given to, okay, is given to a patient to diagnose thyroid activity. The original dosage is 280 MBQ, and after 6 hours, there are 274 MBQ. What is the half-life to the nearest day? Okay, so we have our formula for this. So we're going to write that down. We have our A equals A naught times X and little t over big T. So now the trick is, what do each of our variables mean? So our final amount is 274 MBQ. Now, I personally do not know exactly what that unit of measure is. For now, I'm just going to treat it as since we're using the same unit for this, I think we can safely say that A naught in the same unit, that's our initial amount, 280 MBQ, but we don't really need to know what the unit is in order to be able to solve it, because our answer is going to be in days. So time, I do know units of time pretty well. So I know that hours, and we're wanting to give our answer in half-life to the nearest days, is not the same. So 6 hours, we have, and which of our two t's is that going to be? So we have our little t is the total time the item is left, and the big T is the time of growth or decay. So it looks like big T is the one that we're going to be solving for, and we want it in days. So we also are going to have our little t in days. So little t is 6 hours, but if we take 6 and divide it by 24, it is 0.25 days. So we're going to want to do that all in days, just so that we get a more accurate answer. Okay, any other variables we need? Yes, we need X. And so X will often be given to you as a growth or decay value, but here we don't actually have one. It just says half-life. So that means our X is 0.5, because we want to know when it's going to be half of what it is. So every time you multiply by 1/2, the T and T is the same, it's half, it will end up being half of your initial amount. If you see, that would be T over T would equal 1 when you have a half-life. Okay, so now let's plug in our values. So we have 274 equals 280 times X to the 6 hours, we want 0.25 over big T. And our X is we're actually going to replace that with 0.5. Okay, so now we're going to do 274 divided by 280. And we're going to probably want to keep that a relatively big number. So I'm just going to write 274 divided by 280 equals 0.5 to the 0.25 over big T. We're going to log both sides, so we'll have log 274 over 280 equals 0.25 over T log 0.5. Okay, so now we can divide both sides. Well, we want the t in the numerator. So I'm going to multiply both sides by big T, and then I'm going to divide my right-hand side by log 274 over 280. So my big T is going to be equal to 0.25 times log 0.5, and then divided by log of 274 divided by 280. And then I'm going to crunch that all into a calculator, being pretty careful about my order of operations. When you do log 274 divided by 280, you're going to have to be careful about brackets because you want to make sure that that's all inside the log. So we have 0.25 times log 0.5. Okay, and then we're going to divide that by log of 274 divided by 280, and just make sure we close off our brackets properly. And we are going to get big T equals 7.99976, which is approximately equal to 8 days. So that would be our half-life would be 8 of that radioisotope would be 8 days.